So, thank you, Ma'am Charmaine. So, now let's continue to the 13.3 some 20th century development. So, our first topic is about Amy Noether's story of rings. So, no discussion of 20th century mathematics would be complete without Amy Noether. So, Amelie Amy Noether from 1882 to 1935. So, she was considered the greatest female mathematician up to her time. She was born in the small South German town of Erlangen, where her father, Max Noether, was the professor at the university. So, Max Noether from 1844 to 1921 was distinguished mathematician who played a considerable part in the development of the theory of algebra functions, and Emmy Noether's younger brother Fritz later became a professor of applied mathematics in Breslau. The great traditions of the university was currently being carried on by a quartet of full professors. The name of the full professors was Felix Klein, David Hilbert, Hermann Hermann Minkowski, and Carl Ruge. So in 1907, Emmy Noether had completed her doctoral thesis on complete system invariant for ternary biquadratic forms under the tutelage of one of the most prominent mathematicians at the day and an old family friend, Paul Gordon. So 331 forms written in symbolic notation. She was later to dismiss it as a jungle form of formulas. As an extreme examples of formal computation, the dissertations was entirely in line with the spirit of the earlier work of Gordon, whom his admiring colleagues called the king of the invariant. The theory of algebraic invariant was one of the branches of mathematics much in vogue in the early 1900s. So, Hilbert was working on the mathematical aspect of a general theory of relativity. So 3 years later, she was appointed as Nebenamtiter außerordentlicher professors and unofficial professors extraordinary. A merely honorary titles that carried neither obligation nor remunerations. Subsequently, Emmy Noether was entrusted with a lectureship in algebra, which carried with a very modest salary, the first and only salary she was ever to pay at Göttingen. Norbert Wiener from 1894 to 1964, a professor of mathematics at Massachusetts Institute of Technology. So the mathematics that grew out of her papers following in 1920s and the lectures she gave at Göttingen to the Noether's boys made Emmy Noether one of the pioneers of modern algebra. So, under the influence of Hilbert axiomatic thinking, Emmy Noether saw a system of axioms to rings. So we are indebted to the Dedekind for the terms itself that would allow her to subsume a number in earlier under a general theory. These axioms appear in 1921 in her famous paper, The Theory of Ideal Rings. The theory in ideal rings. So, Noether was not to given under the influence of Hilbert axiomatic thinking. Emmy Noether sought a system of actions of four rings were indebted to the Dedekind for the terms himself that would allow her to subsume a numbers earlier under the general theory. So these axioms appeared in 1921 in her now famous paper definitions of commutative ring. So having been preceded by the Abraham Frankel in 1940 and Masasu Sono in 1970. This operation required satisfy 6 condition. So the first is the associative law of addition. So where A plus B plus C is equals to A plus B plus C. So the second is the commutative law for addition. So A plus B is equals to B plus A. So number 3 is the associative law for multiplication. So A times B times C is equals to A times B times C. So number 4 is the commutative law for multiplication. So A times B is equals to B times A. So number 5 is the distributive law for multiplications over addition. So A times B plus C is equals to A times B plus C is equals to A times B plus A is equals to C times C. So for number 6 is for any A and B in R, there exists a unique element X satisfying the equations of A plus X is equals to B. So these are the examples for the 6 conditions. These are the samples for the 6 conditions. So for number 1, the examples of associative law for addition. And number 2, the examples of commutative law for addition. And number 3, the examples of associative law for multiplication. And number 4, the examples of commutative law for multiplication. And number 5 is the examples of distributive law for multiplication. Let A be an arbitrary but otherwise set elements of R. Then the equation A plus X is equals to A has the solutions in R. Denote it by 0 for any other element B in R. So let theta be the solutions of the equations A plus B is equals to B. Thus, theta plus A is equals to A plus B is equals to B. B plus 0 is equals to theta plus A plus 0 is equals plus A plus 0 is equals to theta plus A is equals to B. So making 0 an identity element for the operations of addition. So furthermore, the solutions of A plus X is equals to 0 will be furnished the additive inverse of A designated by negative A. So the use of real numbers in algebraic number theory was initiated by Cramer in 1844, who found out that he needed factorization to help to prove certain case of Fermat-Last theorem. The principal result was that each non-zero deals in the rings of algebraic integers in a fix of algebraic numbers L could be uniquely represented as a product of finite numbers of prime ideals. This was published in the supplement to a second edition of Dirichlet Lectures on Number Theory in 1871, which Dedekind edited. So a complete theory of ideals for polynomial rings was obtained by Emmanuel Last in 1868 to 1941. He established that every polynomial's ideal is an intersection of primary ideals. Emmy Noethers, in her 1921 papers, The Theory of Ideal in Rings, generalized Lasker primary decomposition theorem to a commutative two arbitrary commutative rings satisfying an ascending state condition for ideals, that is, to ring in which n is strictly ascending for ideals inite. So Noetherian, in second important articles, Abstract Constructions of Ideal Theory in the Domain of Algebraic Number Fields in 1927. So Noether did for abstract rings what Dedekind had done for a ring for algebraic numbers. Namely, she formulated V axioms that ensure possibility of factoring every ideals into a night product of prime ideal rings satisfying this action are known as the Dedekind rings. Van der Waerden spent a year studying with Noether before returning to the University of Amsterdam to complete his doctorate. He was at 22 years of age already regarded as one of the most gifted mathematical talent in Europe. Quickly mastering Noether's idea, he later gave them brilliant exposition in two-volume Modern Algebra in 1930. Reprinted in numerous editions and translated into many different languages. It became the standard work in ELF. A large part of what is contained in the second volume of Modern Algebra must be regarded as Noether property. So, during the spring of 1933, the storm of the Nazi Revolution that modern Black Plague swept over Germany. So, on January 30, the aged and the confused President von Hindenburg resolved a parliamentary impasse by appointing Adolf Hitler to the post of Chancellor. Hitler asked the Reichstag for sweeping power that would allow his government to dispense with constitutional procedures and limitations as it carried through the political moral disinfections of public life. With the passage of Enabling Act on March 23, 1933, Germany's fate was sealed for the next 12 years. Like Sonia Kovalevsky, the greatest woman mathematician before the 20th century, Emmy Noether died at the height of her career. Beyond that, the two female scholars had little in common. It's about von Neumann and the computer. So, development in German university following the spring of 1930 are well known. Mass dismissals of racially undesirable professors took place accompanied by the political appointment and promotion for those who conformed to the ideas of Nazi regime. Robbed at all independence, respected academic institutions were changed into Brown University. Hilbert was left practically alone in an empty Göttingen. The honorable mathematics tradition, first kindled by Gauss, Dirichlet, and Riemann, now broken. Among the scholars of whom the university had once been proud Emmy Noethers, Richard Coran, Hermann Weyl, Otto Neugebauer, Felix Bernstein, Hans Lewy, and Paul Vernies had all taken refuge outside of Germany. During the first wave of emigration that began in 1933, Princeton chose Solomon Bronchner or Munich, Yale Max Zorn or Hale, Venice Iviania, Hans Rademacher or Breslau, New York University Richard Coran or Göttingen, University of Kentucky Richard Brewer or Königsberg, and the list could be extended. So in Princeton, the presence of Hermann Weyl and Albert Einstein made the institution for advanced study something of reception centers for reputed mathematicians and physicists. When the Institution for Advanced Study was founded in 1933, the original 6 professors and its School of Mathematics were J. W. Alexander, A. Einstein M. Morse O. Vivlen J. von Neumann, and H. Weyl. Kurt Gödel accepted an offer of permanent membership in 1938 after the German annexation of Austria. Emmy Artin, Paul Erdos, Kurt Friedrich, Richard von Mises, George Polya, Stanislaw Ulam, Andre Weil, and Anthony Sigmund. By the early 1930s, American mathematics had gradually evolved into a collection of formal abstract specialties detached from the physical substances. The newcomers were instrumental in creating major research programs of an applied natures of several universities, most prominent at New York University, under the guidance of Richard Courant in 1888 and 1972. Richard Courant had been the director of Göttingen Mathematics Institute since it was established in 1929. So on April of 1933, he was one of the 18 men who, because they were Jewish or had Jewish wife, were summarily dismissed, placed on leave from the institute. In the immediately post-war years, Coran established the school institute for mathematics and mechanics, with the accompanying journals, Communication for Pure and Applied Mathematics. In 1952, the Atomic Energy Commission selected New York University as the site of its only high-speed electronic computer, IUNIFA. On his retirement from the positions in 1958, the capital's Applied Mathematical Analysis was formally renamed the Coran Institutions of Mathematical Sciences. John von Neumann in 1903 to 1957. So he was born in Budapest, Hungary, the eldest of three sons of an affluent Jewish banker. In 1923, the Federal Institutions of Technology in Zurich, he was also an undergraduate degree from the Zurich Chemical Engineering in 1925. PhD Mathematics from Budapest in 1926. A private docent at University of Berlin from 1926 to 1929 and one in Hamburg during the academic year in 1929 to 1930. Working at a prodigious rate, he developed the mathematical foundation of quantum mechanics great game theory as full-edged discipline, proposed a set of axioms for the set theory quite different from those of Zermelo and Frankel, and extended Emmy-Noodle's algebra to the study of rings of operators, now called von Neumann's algebra. In 1933, he was invited to become one of the original members, the youngest of the newly established Institute of Advanced Study. 28 paper Sir Maurice der Gesellschaft PL's Theory of Parlor Game, Neumann initiated the mathematical study of games. They believed that certain competitive economic situations could be effectively modeled by suitable games of strategy. The result of their collaboration was now classic 600-page, The Theory of Games and Economic Behavior, which appeared in 1944. A major step toward comprehensive mathematical economic was a short Princeton PhD thesis entitled Non-Cooperative Games, written by John Nash at the age of 21. Nash's dissertation was only 27 pages long and did not seem to be particularly meritorious at time. Von Neumann labeled it as trivial on the first reading, but it would later earn him the 1994 Nobel Prize in Economics. He was appointed also a member of Atomic Energy Commission in 1954, retaining the positions until 1957, the year of his ultimately death from the cancer. In 1946, he proposed the Institute for Advanced Study built a computer whose unprecedented speed and power would leapfrog all devices then existing or being planned. The machine, AIS, as it would leave calls, was working order in late in 1951 and used effectively for scientific computation throughout the 1950s. A duplicate of von Neumann's computer later deployed at Los Alamos was known as MANIAC. MANIAC means Mathematically Analyzer Numerical Integrators Atomic Calculator, but more affectionately called Joniac in borrowing from von Neumann name. From 1926 and Walter Fate in 1930 to 2004. So first, let discuss about Peter Lacks. So Lacks was born in the Budapest, Hungary. He and his parents were shipbound for New York when the United States entered the Second World War. In 1951, Lacks joined the university faculty and rose quickly to become a professor 7 years later. He served as a director of the Koran Institute from 1972 until 1980. The Norwegian Academy of Science awarded its Abel Prize to Lacks in 2005 for his impressive contributions to the theory and applications of partial differential equations. Let us discuss about Walter Fate also. So Walter Fate was born in Vienna. So 2 days before the Second World War began in 1939, his parents put him on children's transport, the last train that was permitted to take the Jewish children out of the country. He received a master's degree from the University of Chicago in 1951 and was awarded a doctorate by the university. Fate settled permanently at Yale University in 1964, where he remained until his retirement in 2003. In 1963, Fate and his contemporary John Thomson won international acclaim for the resolution of a 50-year-old problem in group theory called the Burnside odd order conjecture. Burnside in 1852 to 1927 had given the first comprehensive treatment in English of groups theory in the theory of group of finite order or orders, signifying the numbers of elements in a group. So in the first edition of this classic work, which appeared in 1897, Burnside remarked that no non-commutative simple group of odd order in the present known to exist. So a simple group is one which has no normal subgroups other than the whole group itself and the trivial subgroup consisting only the identity elements. Second editions of Burnside textbook was published in 1911. He had examined the 9 groups of order less than 40,000. So non-commutative simple group of odd order do not exist. Prophecy was confirmed in Fate Thomson paper in 1963. So their proof requires a full 255 pages issue of the Pacific Journals of Mathematics. Many view it as the most influential article ever written on the theory of finite group.